Hi, my name's Rebecca Simmonds and I'm currently a Research Associate at Newcastle University, finishing off my PhD. I'm here to talk to you about Scalable Geospatial Indexes in Cassandra with my colleague Jonathan from RedHat. So I want to talk to you first about a few of the things that I've done. So I've been working on a system to analyse social media, specifically Twitter data, scalably using Cassandra at the back end. So the idea is that we have this real-time analysis on the top, but then Cassandra underneath to do this historic analysis so that we can get queries back in near real time to be able to combine the data. I also involved in some research projects with a research project called SIDE, which is social inclusion in the digital economy. Here I do some cross-disciplinary projects. So I've worked with geographers and psychology students to combine the system that I'm actually working on with being able to analyse the data for real use cases. So we started off the project by looking at different metadata of tweets, so things like hashtag and the timestamps. We also obviously looked at geolocated data. Now, working with geographers, it was obvious that geolocated data was going to be quite a hot topic between us both, and that's why I focused on it more. Also, Jonathan was quite interested in geospatial data, so that's how we all ended up working together. So we've been working on a project that looks at a collection over 6 weeks, and it collected tweets around an event called Idaho. We ended up collecting 10.5 million tweets, and the problem was being able to visualise this data for different disciplines to actually analyse it. So obviously starting to think about this, each tweet has a geolocation. So you've got a latitude and a longitude. So it's already two-dimensional and quite hard to actually deal with. If you think about storing this as a single point, this is no use at all. You can't go through every single point in the database checking whether it's the correct one. So this led me to think about bounding boxes and basically dividing the geographical area into different bounding boxes and then using the points in that bounding box as a key. However, if you're going through each bounding box, once again, it's taking too long, too many searches, it's not in near real time, and it can be quite difficult because you're bringing back a lot of data as well. So this led us on to using a different structure in memory to be able to cut down the searches that we were doing. So we've used a tree structure. So there's different ways we can use this, and Jonathan will talk about this a bit more. I'm just here for the demo. So basically, I wanted to now show you the demo. As you can see on the screen, through the web browser, we're on Wi-Fi, so I'm hoping that it works. As you can see, it's a map, and I've zoomed into London. Each of the numbers shows a cluster of tweets, so there's the area of that one for the cluster of tweets. These, as you zoom in, should go down to individual markers so that the user can look at each tweet, the information provided, and be able to analyse that. What we've done with this demo is we've also added in another dimension, and we're looking at time as well. So not only have we returned all of the markers for this geospatial bounding box, we've also used time in it. So if you click on this button, we get a lovely graph that shows you the 6 weeks of data that this area has collected. It shows you the rate per day. The geographers were particularly interested in that because they like to look at different areas and seeing whether people are actually tweeting, especially more deprived areas that might not have the money to get the technology. They like to see whether people were. When we analysed this sort of data in Newcastle, it turned out that people were actually sacrificing quite a lot just to be able to post tweets. So that was quite interesting. So then, if you click on one of the bars, so this is the 19th to the 5th, worked. It then changes all the data for just that day. So that's all of the data for that day within that bounding box. You press the play button, you get a nice sweep through the data of each day. As the bars carry on going, it's adding more and more data as time goes. So the hope is that we can use this for topics as well and being able to see the spread of information. So using this technique and using the underlying the system in memory that Jonathan will talk about, we've actually managed to get the responses so quick that we're now struggling with putting the markers on in the browser, and that seems to be the bottleneck at the minute. So I'll pass you over to Jonathan now.
Thanks. Hello. Give me a moment to wrestle with the technology here. I need to mirroring back off. And yes, that looks good. All right, hello. I'm the RedHat half of this partnership. So how many of you are here because you've got some kind of problem like the one we just saw, where you've got a vast amount of data, and some part of that is a spatial element, some kind of location information, and you need to index it? How many people does that describe? A good chunk of the audience. What on earth are the rest of you doing here? Okay, so the case I wanted to solve was that more and more of the data that's coming in has some kind of spatial element to it. Particularly now we're seeing data coming in from sensor networks. Anything and everything can be instrumented. You already are, because you're carrying around a mobile phone that's got location sensors in it. And we want to be able to query this data efficiently. So the dimensions of who did what and when they did it, those are fairly easy. They're linear things. So already built into Cassandra is the ability to handle that kind of data. Anything that can be put on a line is easy. Locations are more difficult because they're inherently multi-dimensional. So in the simple case, a location is just 2 dimensions, x and y. And a geolocation is differentiated from a general location just by being expressed in terms of latitude and longitude. You can add an extra dimension if you want to capture height, although many applications don't need it. And as we'll see, you can also add in extra dimensions to the same index to capture things like time, as we saw in the demo. So there's an increasing need for this kind of thing, and I wanted to look at whether Cassandra was going to be a good platform for that kind of indexing. So historically, there's been this view that Cassandra is essentially a huge index construction kit. It's a toolkit for building exactly this kind of thing. So at first glance, it should be a very good tool for this kind of job. Indexing the built-in types is pretty much done for you. So column families are inherently distributed index-organized tables, so they just work. Great. It was recognized that full denormalization is not always the way to go. So since version 0.7, which is a while back now, we've had secondary indexes, and it's become known as kind of a sweet spot for those. You don't want to index things that have very low dimensionality or very high dimensionality, but that still leaves you a lot of wiggle room in between, where secondary indexes are a great tool. The problem is that Cassandra doesn't really understand anything about spatial types or relationships. So we're going to be able to reuse some of this functionality, but we're going to have to add on some new functionality as well to be able to handle index of spatial data. Fortunately, that's exactly the kind of thing I like doing. I like open platforms that are toolkits with extension points. So let's look at what's already there that might be useful for this kind of problem. SQL seems to be the way forward. How many of you are still using Thrift? Just out of curiosity. A few, okay. The early adopters are kind of saddled with it. They went into production early and have systems that are very stable and work fine and keep using Thrift. But for people who are not yet in production, who are still looking at it, I think CQL is the starting point these days. User-defined types, mentioned briefly earlier today. They're already there in 2.1. Asynchronous queries is another one I want to touch on. If, like me, you come from a JDBC background as a programmer, you're used to a database access API that's inherently synchronous. But using an asynchronous API brings you certain advantages, particularly with the distributed nature of Cassandra. So that's what we have now as building blocks, but also looking forward to new things coming in 3. So Jonathan Ellis has hinted at a couple of these, and if you were in this room for the previous session, you saw some of the user-defined functions work that's going on. Distributed indexes also look very similar to tables, but there's code inside Cassandra to keep them in sync. So what can we use from these suite of building blocks to allow us to model spatial types easily? User-defined types, Great way to extend the type system inside the database. So you can define new types. In this case, we'll start by defining a point, which is simply an x and y coordinate. And if it's geospatial data, that x and y would be latitude and longitude. Just to make life difficult, by convention, lat and long the other way around, you put the y coordinate first. Don't ask. So user-defined types work well with the Cassandra toolchain. Historically, if you wanted to do this kind of thing, your only option was to do the serialization in the client, use protobuf or whatever your preferred format is, and then you're essentially writing a blob to the database. And the database can't look inside that blob. It has no native understanding of what the content is. So that's a bit of a pain during the development cycle. You can do things like query it in CQL, but what you get back is just a byte buffer. And if you're doing that in CQL-SH, it renders it as a hex string, and it's kind of meaningless. So what you'll notice as you transition to using this new feature is that suddenly the tool chain helps you out much more. If you do a query in CQL-SH against a type, it'll render it in more or less JSON format for you in the shell, so it makes debugging a lot easier. You can key on them, so this is similar to what you would once have done by concatenating together several columns as your key, but the database will just handle it for you now. Don't ask me why they introduced this frozen term. Apparently it's not a marketing tie-up with Disney, it's something to do with keeping the type stable in future versions. So schema evolution is going to be an issue here. I think for simple types that aren't likely to evolve, like a point, you're probably on safe ground. It's less clear to me, frankly, how this is going to work with complex types like mapping entire JSON documents into a type in the database, where you need to evolve the schema over time. But right now, that's a great start for us. We can define points and work with them natively in the database. But points only really allow us to do exact match lookup. So if events are all happening at exactly the same point or group of points, that's fine. But events are kind of messy and happen all over the place. So we need a new construct. We need an area or a bounding box. So I've chosen to express that as a pair of points, two diagonally opposed corners of the box. There's other ways to represent boxes, of course, but that one's the simplest. And this just shows that you can nest these types now in the database. So you can have arbitrarily complex structures built up of other types. And of course, you can include primitives inside these types as well. So that gives us the two basic constructs we need in the database. Now, how do we actually build an index out of these? Well, what we're going to do is we're going to take our coordinate plane, whatever that is. If it's the surface of the Earth, for example, we've got latitude and longitude, and that gives us essentially a grid that we can break this down into. So we're going to divide up our surface into what essentially is a piece of graph paper, a piece of squared paper, little regions, grids, all the same size, cells. So any event happens inside one of these regions, according to its latitude and longitude. So this allows us to take a vast number of points and map them down into a smaller, finite number of buckets or regions. So our index is going to look like region, that's the container for the events, the specific location, the point where they actually happened within that region, and then some bit of data. So if we're treating this as a completely organized, index-organized table, the data will be a serialization of our entire event structure, but it could equally well just be a UUID key into another table. So this is the fundamental building block. What we've got here is a distributed index, essentially. So any particular event is going to be assigned to a region according to where it happened, and that region in turn is a primary key, so it's assigned to some part of the Cassandra ring, a physical node in the ring. So then we have all this data inside Cassandra. We need to be able to search it. So for many applications, like the demo we saw earlier, what you want is a visualization. So you've got a particular area of interest, a bounding box that defines the area in which you want to retrieve events. And you need to find out what the correspondence between that and the underlying grid you've got in the index is. So you need some kind of function in your client that is just going to calculate which cells in the index, which regions in the index overlap this bounding box of interest. And that's going to give you back a list of regions. And then you perform an inquiry against Cassandra. So this is just a query where you say, give me back all the data from my index, as long as the condition holds the region for that event matches one of the regions of interest in my list here. The conventional way to do this is with a single statement, as you see there on the screen, and that fans out from the coordinator. So client to coordinator is a single statement, and then the coordinator breaks it down into pieces and sends it to each of the nodes that owns one of these regions. So potentially that's up to the size of the number of regions you're querying. That's the number of nodes you hit. So you get some degree of parallelism there. What we found when you tried that is that there's quite a lot of latency involved in that process. Well, relatively speaking, Cassandra's still very quick, but not quite as quick as I wanted. So one of the techniques we got quite interested in was decomposing this on the client side instead of letting the coordinator do it. So if we take this in clause, and instead of sending it direct to the database, to the CQL parser and the coordinator, we write in the client a number of selects, each of which is an exact match for one region instead of a list of regions. And then we give that to the driver. The driver is smart enough to know the ring topology and to send each of those queries directly to the node that owns the data. So the coordinator becomes the data-owning node for each of these. So that eliminates an extra network hop. It also means if we can fire these off in parallel through the asynchronous API in the driver, that we start getting results back much sooner because one of these regions will respond very quickly. For example, if it has a few items in it or if it's on a particularly powerful or lightly loaded node, that allows the client to immediately start dealing with that result set. Instead of having to wait for the coordinator to assemble all the results from all the nodes, where obviously your latency is bounded by the slowest node. So we saw here a great reduction in tail latency. Unfortunately, we also saw an explosion in the amount of code we had to write in the application. There is an asynchronous API. There's a fairly good blog on the DataStax website about how to use it if you're using the Java driver. But it does involve some additional plumbing, which in my view really belongs down in the driver. It's just not there yet. So this is one of those cases where you start tuning. You can write the basic app very quickly, get something running. And if the latency is not quite where you want it, this is the kind of technique you can do to optimize it a bit. So that gives us a result set, but it's not an exact match for what we want. And the problem here is that the viewing area, the bounding box that we're querying, so that's what the user's got on their screen, doesn't always conveniently, indeed almost always doesn't line up with the index grid. So we need to do some further filtering here. We need an operation that's going to say, yeah, we know it's in the right region, but part of that region overlaps the area of interest and part of it doesn't, so we need to filter a bit further. We need this contains operation. And ideally, we'd like to do this on the server side because that saves us having to move all this data to the client. And also, we've got much more processing resource on the server side. We've got a parallel cluster there, whereas the client's a single node, and it would have to do all the work. So theoretically, we should get much better performance if we can push this to the server. There's no native way to do it yet. If you were here in the previous session, you would have seen a preview of functionality that's coming down the line to do this using user-defined functions. It's not there yet, but I'm kind of impatient, so I started poking around to try and figure out how to do this in the existing code base. And it turns out there's an extension point called Query Handler. Has anyone actually played of this or is even aware of it? Oh, yes. Yeah, okay, one or two. That's about what I expected. It's not been well publicized, but it's very powerful. It allows you to intercept the CQL string that's sent to the coordinator and essentially rewrite it. So you can completely replace CQL if you like. But what I wanted to do was simply extend CQL with a new keyword, a new method, effectively, that would allow me to pass the filtering parameters down to the node that's handling the coordination, the CQL parsing, which, because I'm using the asynchronous API and decomposing on the client side, is also the data owning node. So that involves a fair bit of work currently. Hopefully it'll be much, much less work once we have user-defined functions in version 3. But again, it's worth it. If you have this kind of performance issue, this kind of problem where you want to do some sophisticated filtering and you can't currently express that in CQL, it's well worth looking at what you can do to to move that to the server because it will bring down your tail latency substantially. The reason there's such a big range here, from a very modest improvement through to a quite substantial one, is to do with the resolution of the grid. So if you have a grid where the cells are roughly the same size as the area of interest you're querying against, that's great, but in some cases you can have cells in the grid that are much, much larger, and in that case a lot of them doesn't overlap, so you can eliminate quite a lot of data at the server side with this server-side filtering technique, and in those cases you see a much bigger improvement. So what you're really measuring is the proportion of data that you can eliminate at the server. And of course, once you have this technique, you're not just limited anymore to using the contains method to test whether the point is inside the area of interest or not. You could push additional filters down to the server. So you could push a filter that was based on some other characteristic of the event, such as the user or the time. So we see that there's a huge range of results we can get there according to what the grid resolution is. So clearly this is a critical tuning parameter for this kind of application. And the fundamental trade-off you're looking at is that the number of grid cells determines really your parallelism, because you're dealing with wide rows in the database, your partition key is the grid cell. So essentially each disk seek, each unit of disk scanning is the grid cell. So more cells is better. You've got a lot of irrelevant data in big cells. If you make the cells smaller, you get less data to filter out, and therefore it's quicker. You're reading less off disk than reading data off disk and then just discarding it is kind of a waste. But at the same time, you want to keep the number of disk seeks down. You don't want a huge number of cells because your disk head's going to be jumping around all over the place, and that's going to slow you down a lot. It's typically the bottleneck in Cassandra read operations. So from that point of view, well, fewer cells is better. You still want enough to keep all your disk spindles busy, but you don't want really more than that. You don't want to be doing more than one seek per disk if you can help it in a query. So what you'll notice as you try to build this kind of application is that some of them have a natural resolution that suits it quite well, but more often than not, it's query dependent, as with so many things in Cassandra. So again, denormalization is the way to go. Cassandra's built on this idea that you should have a column family that suits each of your queries, that structures the data in a way that suits the particular application or sub-application query that's going to hit that table. So simply build indexes that have different grid sizes. If you want an application where the user can zoom in on a map, you've got maybe half a dozen different zoom levels, simply build an index for each one of them. Caveats to that, if you have a vast amount of data, as so many Cassandra applications do, what you'll find is that the coarser grained ones, the ones where you're zoomed all the way out and can see the entire surface of the Earth, very, very cluttered visualization, almost useless. So there, look at ways you can pre-aggregate the data. So I was on a property website the other day, for example, looking at new houses, and one of the things it does in cluttered city center locations is if there's an apartment building, it pre-aggregates all the places for sale in that building into a single marker on the map. So it's a two-level aggregation. You can see on the map which buildings have apartments for sale, and then you click on one and it'll bring up a separate tab with the list of properties. So that kind of technique can help reduce the clutter in your visualization. And it reduces the number of items in the index as well. You've effectively got a two-level index between things that are rendered spatially and then things that are tabulated separately. The other reason you don't want to make these grid cells too big is for the write load. If you have a grid that spans, say, a big city and you're doing social media analytics, a dense population center like that's going to generate a lot of data, and that's all going to go to one physical node in the ring, and that's going to cause problems. So you want to sometimes break down busy cells like that into smaller subcells to help spread the load across the cluster and avoid hotspots. So this skew is a huge problem for geospatial applications, particularly anything that's user-generated data. Just think about the cities versus the oceans. You've got huge tracts of the Earth's surface where basically nothing happens in social media terms because there aren't any people there. And then you've got cities like London, New York, where a lot happens. So a fixed size grid, although it suits visualizations quite well. It's the right technique to use if you're rendering things on a map at a particular resolution. It's not always the best structure for other reasons. So sometimes tying together these different resolution grids into a tree structure is worth considering. So if you've studied computing science, your idea of a tree is probably based on the B tree. Each parent node has 2 child nodes, and they're balanced. And the reason they're balanced is that the performance of the tree is proportional to its depth. The kind of tree structures we use for geospatial data differ a little bit. First of all, you're going to divide the tree based on this nested grid. So your top level grid is going to be, well, let's use geohashing, which is 32 cells. And each of those is going to have 32 subcells and so on. So you're not dealing with necessarily trees of 2 children. It's an arbitrary number of children according to how you want to build your grid. But also they're no longer balanced. In areas where you have a lot of data, you want a deep tree to help split that data amongst several nodes. And in areas where next to nothing happens, you can afford to keep it in big lumps because there's relatively little of it. So this is going to add some complexity to your application. It's one of those things you do at the end. If your performance isn't where you want it to be, it's an optimization technique you bring in because it does add a lot of extra work to the code. And the reason for that is the tree splits. So you have a node, you start off, it's empty, you fill it up with data, and at some point you say, okay, this one's getting too big now. It represents a geographic area of a big city, and I've got lots and lots of data for it. I want to split it into 2 or n subcells. So in a KD tree, you're split in 2 ways. Quad tree 4 ways, geohash 32, take your pick. There's not a lot to choose in performance terms. But to do that split, because the structure is distributed, you need some kind of locking or caching mechanism. And this is where the extra complexity comes and bites you. You can do distributed locking. It tends to be rather slow. It's not my preferred method. My applications tend to be able to tolerate a little bit of temporary inconsistency, so I go for a caching solution where I keep the tree structure in the client. So when a split happens, there's a period of time during which the client has a stale cache because it only sees the parent node until it refreshes its cache, and it's going to keep writing to that parent node and querying from it. But meanwhile, other clients that have different cache timeouts might already have started writing new data to the child nodes. And that's a problem because my client's not going to see them. It's not looking at them. So I can actually solve that one using a vertical slice through the tree. Because I've got all this lovely parallelism, I can use asynchronous queries in the API. I can simply query all the different resolution grids. So I can query the parent and potentially the children. And if the children don't exist yet, because there's been no need to create them, Cassandra will simply return an empty result set. And that's very cheap because the Bloom filters will just say, oh, nothing there. Because we're keying on the grid cell as the partition key, the Bloom filters help us out a lot there. So the read side's not too bad. We can just pay a small extra CPU and network cost to have Cassandra handle that using the Bloom filters. The problem is the writes, because you need to write to the correct depth in the tree. And if some other node has created a split and created child nodes, and your cache is stale, you're still writing to the parent. You don't want to check each time for the structure of the tree. That's very, very expensive. Read before write is considered an anti-pattern in Cassandra. So you want to avoid that if possible. And there's various ways to do that. If you happen to have some kind of event bus set up already to your clients, you can simply send out a notification that the tree structure has changed. I did it instead by polling, so I've got a cache in the client. I write to the parent node until the cache timeout, and then I go and refresh my tree structure from the database and start writing to the children if they exist. And because of this, because the reads are going through a vertical slice in the tree, other nodes, even with a stale cache, still see my reads immediately. It's just that I'm not writing them to the optimal location until the cache times out. So as you can tell, it's kind of hairy, it's complicated to code, but it does work fine. Plays to the eventual consistency strengths of Cassandra with this index design. Phew, okay. Last topic, cloud. No presentation is complete without some mention of cloud, but this one's rather obscure. This is a ship called the Flying Cloud. Does anyone know what she's famous for? No, I didn't think so. Nor did I until a little while ago. So the Flying Cloud was a sailing clipper in the 1850s, and she became famous for setting the speed record from New York to San Francisco, which in those days meant going all the way down one side, across Cape Horn, and all the way up the other side. It took an average of 200 days. Not exactly a pleasure cruise. Flying Cloud did it in 89 days, less than half the average time. And this is relevant, I promise. It's relevant because the way she did this was based on the work of Matthew Morey, who was a sailor, although not on the ship. He worked in the Depot of Charts and Instruments for the US Navy, what's now the Naval Observatory. And they were essentially the IT department of their day. They looked after all the data from the Navy, looked after its clocks, its chronometers, looked after its charts, but also was the repository of logbooks from all the voyages. So Matthew Morey is what we would now call a data scientist. He went through all these logbooks and he aggregated all the observations of wind and weather. And his data is actually still available today. Here's a visualization I found on the web. This is a great example of Skew, by the way. The continents are completely black because there's no sailing data for them, obviously, and the oceans are populated with data. And this is voyages of the US Navy from about 2 decades. So he published this as a kind of almanac, a book that allowed navigators for the first time to look up a particular route, and indeed a particular time of year, and say, I'm going from A to B at this time of year, where the wind's going to be strongest, where the current's going to be in my favor. And suddenly, instead of relying on word of mouth and their own experience, they had empirical data in a handy reference form. And that's what allowed Flying Cloud and her successors to cut the journey time so much. So a great example of a game-changing use of data analytics long before Cassandra and Hadoop and all the modern tools we take for granted. This was all done with pen and paper. So I rather like that story. I like the idea that data analytics can radically change the domains it's operating over. So, quick wrap-up, and then I'll let you go to lunch, I promise. In my view, the features we have now, CQL, the forthcoming features, particularly in terms of distributed indexes, global indexes, can make Cassandra a very good platform for geospatial indexing. Getting the performance does still take a little bit of work. You might be lucky, you might not need it. Do the simplest thing that you think will work and then start adding the complexity a piece at a time until you get it to perform well. And keep in mind what Matthew Morey did. He built a data analytics app that enabled the Flying Cloud to set a record that stood for actually 136 years. So if you get anywhere close to that, you're doing really well. If you manage to build something that gets you remembered at a conference next century, great. All right, that's it from me. Thank you very much. Have you got any questions? Yes?
What did you find that there are advantages over just straight geohashing indexing in terms of the tree structure? Were there performance advantages there?
Well, geohash is essentially a tree in that you can have as many characters as you like in it. And you're saying, would you go straight to the narrowest resolution? And
I guess, I mean, if you're denormalizing, you might just store it at 3 or 4 different levels of geohashing.
Right.
Did you experiment with that, or did you?
It does depend on your scale. The tree structure is essentially an optimization that is necessary where you have a vast amount of data and very high skew. So if you're in more modest territory, the kind of thing that's just barely bigger than what you would do with a relational database, if you're using Cassandra, say, because you want the availability characteristics or the replication characteristics rather than the brute scale characteristics, then yes, you can get away with the simpler model of just denormalizing, with the exception of, obviously, the root level where it gets very, very hotspot, and you probably don't want to denormalize for a grid that's 4, maybe even 30. The root level of geohash is 32 cells. You might get away with it, but 1/32th of the world's surface might unfortunately cover 2 or 3 big cities, and then you're in trouble. If you have a vast amount of data, if you're trying to index, say, the entire tweet fire hose, and by some miracle it's all geo-referenced, it isn't currently, a tiny proportion of it is, but we're a few years away from all of it having geolocation data on. At that point, yeah, you probably do need the tree structure. But come back next year, we'll have a new suite of tools in Cassandra to do more advanced versions of this. It'll get easier over time. Right now, it's early days. You have to build more of the building blocks yourself. But more and more of this will get baked into the engine, and it'll become simpler.
Is the code open source?
Not yet. I hope to get enough free time to polish it up enough to put it out there. Whether my job allows for that or not, I don't know. Ask for it, please. If there's people clamoring for it, then yeah, that incentivizes my boss to say, yeah, people want this, we'll give you the time to do it. So pushing more of this functionality into the engine. Okay, so there's generic things that are not specific to geospatial. They're usage patterns that work regardless. So the Java driver support for parallel query, I would love to be able to hand it an in-query, but also a flag that says decompose this on the client and handle it for me, rather than forcing me to write all this Java code with features and yeah, that kind of thing I think is a great candidate for pushing into the driver or into the engine. Some of this is already happening. I mean, I've been proactively looking at what you can do with server-side code for a while. If you were here for last year's talk, when I was talking about doing top K calculations, I was using something called introvert, which was a way of taking Vertex, which is an async application container, effectively, and embedding Cassandra in it to give it some kind of query capability, some kind of server-side processing capability. And we're seeing that, Introvert itself didn't really take off, but it proved that there was a need there, a use case for this, and that's led to work like Robert Strutt was showing on server-side functions. So I think more and more of that is coming through already. In terms of the geospatial itself, I'm not convinced how much of that belongs in the engine. It's still a bit specialized. It would be a low priority for the core developers right now, I think. That might change over time as more and more people start saying, oh, I've got geospatial data, what can you do to help me? But it might be that also we see some kind of rich client library growing up. So this, if I ever open source this, it might evolve into the de facto client add-on for doing this kind of work.
You talked about the fact that a server-side filter can constrain the amount the data stream going back to the client. But you're still paying for the I/O on the server, aren't you?
You're still paying to read off disk. There's several bits of I/O. There's the disk read, which obviously is expensive, particularly for on spinning disk. There's a network transfer from there to the coordinator, and then there's the transfer from the coordinator to the client. Now, because I'm using this decomposition pattern in the client where I take my in clause and I break it down into queries that the driver then sends direct to each data owning node, I've eliminated the hops through the coordinator already, so that network I/O is gone. But yeah, I'm still pulling things off disk and then throwing some of them away, and I'm getting away with that because I'm still doing a single seek. It's a sequential read that I'm then throwing things out from. It would be worse if I was doing random hops and then throwing away the result of that. But
so that's a tuning exercise. So
it is,
yeah. Stuff is cached,
yeah.
And
so what you see happening sometimes is that if your grid is at too fine a resolution, you have a vast in clause, thousands and thousands of potential buckets, and a lot of them are very, very sparse. Maybe one item, or maybe they don't exist at all. Now, if they don't exist at all, they bounce off a boom filter, so you don't pay a disk cost for those. You still pay a network cost, but it's cheap. If they have very, very little data on, then you've degenerated the case where you're seeking all over the place, and that's nasty. So you don't want to make the grid too fine. And that's where having the structure of the tree cached really helps you, because the parts where you need the tree to be deep because there's a lot of data in it, it can be, but you don't make it universally deep because there's lots of it that would be sparse. You want to keep those bits at a higher granularity, coarser granularity, so that you have the minimum number of buckets necessary, basically, the minimum number of disk seeks.
So you're saying you want to stick that tree that you've got actually into a server-side filter rather than client-side?
No, because it's spread out. The tree is distributed across the cluster. So the server doesn't have any inherent knowledge of the tree. It knows the individual nodes of the tree because they're the partition keys, but it has no understanding what a tree is or how the bits relate. That intelligence is all in the client. There is a pattern in which you make the coordinator smarter. So you make it in charge of the tree. You promote it to being the client of your application, basically. So in the same way that in SQL you send the in clause to the coordinator and the coordinator breaks it down, sends it to the data owners, you could do this the same way. You could put the intelligence in the coordinator, send it the geospatial query, have it understand the tree. That's great if your clients are short-lived or if they're memory constrained, because they don't need to cache the tree structure anymore. They can get all the performance just by relying on the coordinator to do it. Personally, I would follow that pattern by having an app server somewhere that was the client and having dumb clients that talked, REST or something to the app server, which then talked to Cassandra for me. But that's because I'm a middleware guy and I do app servers, right? Your mileage may vary depending on your environment. Okay, I guess we'll leave it there and let you go to lunch, but I'm around if you have more questions. Thank you.